allow me to introduce this issue. I'm Takita from the Fujitsu. What is the purpose of having the quantum computing? And here I'd like to speak about the possibility of using it for the catalyst development. About this, we have the collaboration with the Professor Sekine of Waseda University. So we'd like to share the presentation with him. This next slide, please. This shows the purpose of Fujitsu: make the world more sustainable by building trust in society through innovation. That's our the credo. And here, the kind of proposal I'd like to make is in line with this our purpose of Fujitsu. Next slide. These are the computing technology at Fujitsu. This is a quick summary of what we have done in the area of computing. From 1970, we have introduced Fugaku, supercomputing, starting 1990 rather. And the quantum computing is also a major part. Starting 2020, collaborating with RIKEN, we have been seriously working on the development of the quantum computing, and also the quantum-inspired optimization is also another area. So we can safely say that we are one of the leading companies in Japan. And against this backdrop, in 2023, they were able to issue to release the 64 the qubit, and then on the 22nd of April, we were able to make it 4 times bigger, which is the press release of the 256 qubit the technology. And we have the press release, and we have a booth to show that. We'd like you to listen to what we have around here. So we have been working on this as well. And this slide shows the kind of approach and the Fujitsu's strategy for quantum computing. This is the overall picture of what we do. I talked about the actual machines, and other than that, we've been covering platform software, the control areas, and also the quantum application. This is something I'd like to focus on in my presentation. So we are covering the wide areas, and today I'd like to speak about one of the quantum applications for which we have joined the research with Waseda University, which is the development of catalysts. Moving on to the next slide, I'm sure you are all familiar with the quantum and classical hybrid application. We have listened to the presentation in this area, and the Fujitsu do not believe that it is possible to have the actual application with the quantum application alone. So it is important to to combine this the technology with AI or other optimized computing. So only with that we will be able to come up with something marvelous. And Fujitsu is seriously tackling with the quantum computing, and also on top of that we have some strengths in the areas of the AI and also the optimized computing. So that we are able to make some proposals, and one such areas is the development of the catalysts. So we'd like you to read this. This is about the catalyst development, but we have to go back to the initial question of what the catalyst really is. Try to remember the manganese, the oxide, added on to the oxygenated water, and then you are able to see the oxygen generated from this. So as you can see, this is it's a substance that accelerates a chemical reaction. So with the H2O2, you have the certain the catalyst, and then you are able to have the CO2. So we have we have for example CO2 and also CO, and then if we are able to, or hydrogen, this is the non-toxic. So the kind of the reaction that we are or reaction we'd like to drive is something that is not toxic. So we have to create the high performance catalyst, and so this is not simple. So as can be seen in in the yellow part, the surface of the catalyst is crucial. We have to understand what part of the surface is needed. So we continue utilizing this term of the surface structure modeling. And as can be seen, it is important to note that the most important part of the catalyst is the surface. So there should be some adsorption of the materials onto the surface of the catalyst. So the surface structure modeling is just that. And then so I'd like to speak about how we are able to utilize quantum Fourier transform systems. So we understand that, and then we use the term the adsorption simulation, how atoms and molecules adsorb onto the surface. This is quite key. So that's something we'd like to explain utilizing this. So I talked about two things, and then you put this in this order. What is interesting about this is that on the left-hand side, we have surface structure modeling, and then this way we are able to understand which part of the surface can be used. So you see this kind of a structure, the snowman, and then if you are able to utilize certain surface of the catalyst, and then that means that you are able to use this for the purpose of the material searching. So this is quite and we were able to do that in a very short while, and this kind of material exploration is now made possible. And first is about the surface structure modeling. First, when we say surface structure modeling, allow me to repeat myself. You have the green and blue, the green and the also red and the white. This is the structure of the molecule, and then which part is needed. In what way are we able to reach the necessary the surface? So the electron beam should be applied to the material, and then this way you are able to see the the nature of this. But again, this is if we have to do the experimentation, not quite. If it is possible to utilize the calculation for utilizing quantum, the Fourier transform, that would be much better. So that was a starting point of our research. So we tried to identify the surface. So we have the TFT, which is the classical method, and I'm sure you have talked about this in your presentations, as can be seen on the right-hand side. The x-axis shows the number of computation, the number of hours for the computation, and then when the size goes bigger, and then you go to the right-hand side for the DFT, EFF, and then in that situation, we will see the exponential growth of the time required for the computation. But in the case of QFT, with a log scale, you see the increase of the size, and then you are able to see the acceleration of speed. That will be better, much better. But are we able to have the outcome driven from FFT like the approaches? That's something we wanted to look into. So let's take a look at the image. So this is a surface structure model. Why is it that there is the acceleration? So simply put, for example, if you look at the periodical nature, you have to look at the senses, and then in the case of the classical model, and then you have to have the periodic chart, and then in the case of the qubit, then log to the second power is needed. That's if you are talking about 3D, and then only 30 seconds are needed. So this way we are able to have multiple dimensions, and also in the case of the Fourier transform. And then if there is a small number of atoms, then you are able to utilize S gate and T gate. But if you see the increase of the number of the atoms, then you have to have the control bit. So implementation of the control bit is also necessary. So if we try to be meticulous in this, we would be able to consider this. So on the right-hand side bottom, this is you see the periodicity, and then if you are able to see the periodicity, then it is possible. And so you see the circles, and then you see the peaks for the quantum bit. So that's the goal that we try to imagine in our brain, in our mind. Please take a look at this graph.
Left-hand side is basically X and Y axis for 8 layers by 8 layers. just an image in the middle. Accurate calculation of a periodicity like DFT and FFT. So you can see the results are basically equivalent between A and B and also C. So looks usable. On the right-hand side, well, the result in the middle was not that easy to achieve. In order to get this result in the middle, before QFT, flat top function had to be introduced as a window function, and then the result was aligned with the result from the classical method. So this kind of tweaking is needed for QFT, and if you do that, the calculation would work well. This is what we found out. And that's what we're showing on the slide. Surface structure modeling looked okay. As a result of all this, it was working. And then we moved on to the second step, adsorption simulation. Once we know the surface structure, how can we look at the adsorption? Let's look at this now. On the right top, you can see many circles. And this is basically based on combinatorial problem. There are about 90 different small circles, which are potential areas where the molecules can attach. And we wanted to optimize the attachment of these snowman-like structures. And all you need to do is list them all up, as you can see on the left-hand side, the exhaustive search. And of course, you can find the optimal solution if you do this, but it takes a long time. But if we do sequential search, if first molecule attached to a certain location, other molecules would have to attach in other places. So with this kind of a sequential search, although it's heuristic, you can shorten the calculation time, but optimization is not guaranteed. So we want to find optimized solution with a shorter calculation time, and this is why we decided to use the quantum-inspired optimization. So Ising model is used as a reference, and the interaction between the two models is easy to reflect in this model. So we had high expectation for this. Now, what kind of optimization model did we use? This is a simple explanation. Left bottom shows that there are about 96 small circles identified as candidates, and 0,1 variable is allocated to each. Once the molecule is adhered, then it's 1, otherwise 0. So this is binary used for modeling. Some locations are easier to attach versus others. And in the first term, we are showing this. So energy should be smaller as an objective function. So smaller coefficient for places where it's more difficult to attach. And once molecule attaches in one location, we have to think about interaction for the next molecule. And this is the quadratic term. And then annealer and quantum-inspired method can now be applied. But this kind of preparation, like surface modeling, has to be done with classical calculation. We have to do all the preparatory steps using the classical method. That is why we call this a hybrid approach. And this is the result of the simulation. 96 potential locations. If there is only one attachment, adhesion, what would be the location? That's the far left graph. Palladium, zinc, and molecules attach between palladium and palladium if there are a small number of atoms. But as it increases, maybe it's in between palladium and zinc or on top of zinc. So the characteristics tend to change. And the calculation actually reflects reality. Graph in the middle shows the objective function. So can we achieve low energy? dA, this is quantum optimization with the lowest level of energy. And this way we verify the performance. Right-hand side shows calculation time. If we do exhaustive search, of course it takes longer, but compared to heuristics approach, dA, the quantum-inspired dA, is actually better. Again, we could achieve a positive result, indicating that the methodology that we were employing was effective. As I have just explained, surface structure modeling using quantum Fourier transform and also adsorption simulation using quantum-inspired approach. You may think this was the end of the story, but actually, no. There is more to do. Somebody else mentioned this today. Once you achieve 1 and 2, it is really great because you have various crystals and you can look at various substructures and do simulation against these structures. And then you end up with a lot of data. You accumulate a lot of data, which means that you can put it into AI and do inference for new materials. This kind of approach was limited to experts in the past, but once this is computationally possible, you can use AI and quantum technology, and anybody can identify a new material. You don't have to be even awake, perhaps. Anyway, we believe that this is a potential breakthrough. So hopefully next year at Q2D, we can report the progress on this, and this is something that we're thinking as a next step. I just wanted to share that with you on this slide. And then surface structure modeling and adsorption simulation were covered in this presentation. And we worked together with Dr. Sekine's lab in Waseda University, and we co-authored the papers. Today, the explanation was pretty much abbreviated, but if you're interested, please look at the details in these papers. And this is my last slide. As I showed in the beginning, through innovation, we want to build, we want to make the world more sustainable by building trust in society through innovation. Sustainable catalyst development breakthrough. This is what we want to achieve. And this is how we can contribute to solving problems that are really important for this industry. And we would like to continuously report the progress back to you. And that concludes my presentation today. Thank you very much for kind attention.